one thing. Second thing, Nadi is going to give a tutorial today. Third, Netta Engelhardt continues to be delayed. So tomorrow there'll be one less lecture. And the tour of the old city will start earlier. So maybe at 12. There'll be lunch here before that. And we'll introduce everybody tomorrow as well, first thing.
Thank you. Okay. Thanks, David, and hello, everyone, again. Let me begin by reviewing some things that we saw last time. One was the computation of the thermal entropy. So we computed it using this trick, so this is the definition in the saddle point approximation. It's some differential operator acting on the on-shell action of JT gravity evaluated on the Euclidean Seagull or the Euclidean black hole. This I JT can be written in the following way. So here the solution just looks like this disk where the periodicity is beta. And then we said that we can imagine quotienting this. There's some smaller angle beta tilde, less than beta, which would give you this quotiented disk. We've introduced a conical singularity plus this branch cut. I'm going to call this picture, where there's no branch cut, the cover, and this picture the branched cover. Okay? And why do we do this? Because if you do this, then the action gets a very simple form, and you can take out the beta dependence. In particular, it's going to be, if you just take this branched cover spacetime with the conical singularity, and you evaluate the JT action on it, you're going to get a singular term coming from the conical singularity. But clearly that's not here on the left-hand side, and therefore you have to subtract it by adding this term here, which is exactly the contribution that you generate from having a conical singularity. So there's that. There's also this factor that I actually forgot to talk about last time. Why are we multiplying this term by this factor? Well, here, this is JT gravity on this entire disk, whose length is beta. But here, this is a smaller disk, beta tilde. In particular, we're missing a chunk of this this bigger disk when we did this quotient. Right? The angle is smaller, and so we just have to rescale it with the ratio of these two angles. And the reason why it's so simple, that it's just a simple rescaling like that, is because the action is local, okay? Or rather, it's the integral of the local density. Okay, and then now we just need to act with this differential operator on beta. These are the only two places that beta appears. And then you take what this does, that it kills this term, and it leaves you with this term, and hence you get that the thermal entropy is given by the dilaton over 4 G Newton. In higher dimensions, the dilaton, oh, sorry, there's no knot here. The dilaton, the analog of the dilaton in higher dimensions is the volume of the transverse directions, orthogonal to the radius direction, and hence that's just the area, let's say in 3+1 or 4-dimensional gravity. Okay, so that was one story. Another story was the technique for computing entanglement entropy. Suppose we want to compute the entropy of a single interval, A, here. The way we do it is we compute it using this replica trick. I guess I forgot to write that. S is equal to the limit as n goes to 1. I think there's a minus sign, maybe. dn trace go to the n. The way to do it is to have n copies of your system that are glued sequentially along the cut representing A. Okay? And basically, each one of these is the density matrix of A, and I'm just multiplying them by each other n times. This is the cover. And then what you can do is you can work on the branch cover, replacing these cuts with this branch cut. You have to go around this thing n times to come back to the original sheet.
This is the entropy of the cut?
This is the entropy, yes, of the interval where the cut is, yes.
So this is only for a one-dimensional interval?
Correct. So here I am considering a CFT in 1 + 1 dimensions.
Okay.
So just living on space. So it's an interval in space. I said, yeah, I didn't derive it. I made the claim that this quantity can be behaves like a 2-point function of primary fields. Okay? The 2-point function of primary fields in a CFT, we know what it is, fixed by conformal symmetry. Then, so this thing is just 1 over the distance between 1 and 2. This is not equal to 1. Delta 2 times delta n. Okay? Delta n depends on n, and that's where the n dependence comes in. And then when you take the derivative with respect to n, n goes to 1, you get the answer for the entropy. Okay, so that was one interval. We didn't talk about this last time, but suppose you want to compute the entropy of 2 intervals. What you do, so here are my 2 intervals. You do the same thing, and you're going to get, the branched cover is going to look like, you have 2 branch cuts. Okay, 1, 2, and 3, 4. And that is going to be given by a 4-point function of twist fields. Okay? And notice that it's sigma n minus n, n minus n. Okay? You can think of those as like charges, if you will. Okay. And again, you apply this once you compute the 4-point function, you apply this and you get the entropy. But 4-point function in a CFT is not completely fixed by conformal symmetry. It depends on the details of the theory. But in certain limits, one can extract universal behavior, and we will come back to that later. Okay.
Question.
Yes.
So is it true that you added this conformal field theory to do a purification of the black hole? So you treat now the whole system of the black hole and the conformal field theory as a pure state. You compute the entanglement entropy of the conformal, and you say that it's the same as a black hole. That's logic?
Yes and no. So the conformal field theory lived everywhere. And so we had the ADS region here, which was gravity plus a conformal field theory. But on the sides, the wings or the bats, I only have the conformal field theory without gravity. The thing that I added were the wings, the bat. Okay? And then the entropy of this can be thought of as the entropy of the black hole because the entire thing is a pure state.
But in that case, you would expect that it will not depend on what you add on this flat part.
What do you mean?
One conformal field theory or another, you should still get the same result for the...
No, I think it depends because implicitly I'm preparing a state in the Euclidean path integral. So remember this thing, the path integral that prepared the state looks something like this. Right? So let's say here we had CFD1 plus gravity, and here we have CFD2. Okay? In the state preparation for the state s equals 0, this path integral mixes everything with everything. The state depends on the details of the state here depends on the details of the 2 conformal field theories. But in the case that we're considering, they're the same conformal field theory. Okay. Okay, so we then had this technology, and we said, let's compute the entropy of some bath region like this. Okay? Just to emphasize the point was mentioned, that because the global state is pure, the answer that you would get for this calculation is the same as the answer that you would get for this calculation. Okay? Where you take these two and you evolve it to the future. Okay? This is about purity of the global state. Now, we computed the entropy of BL and BR. Sorry. I mixed up my left and right. Okay, whatever. And we found that the entropy just grows for all time. So this is the entropy of the LBR. Okay, and then we discussed how this is problematic because it exceeds the Bekenstein-Hawking entropy of the black hole, or of the wormhole, which is twice the Bekenstein-Hawking entropy of a single black hole, because it has two horizons on the two sides. And we talked about the problems of that. And hopefully people did the homework to show that thermal entropy is always greater than the von Neumann entropy. I'm not going to use it, but anyways. Okay, any questions on what we talked about last time?
I'm actually confused with the what is the conformal theory in which you do the calculation that gives you the Italian entropy?
So I have a conformal field theory that lives everywhere.
You do it in that conformal field theory?
Yes.
So don't you lose information about the fact that you also have gravity on top of that in some of the regime?
I am using, there's a simplification that happens here in that gravity is taken into account and it does not change the answer. Well, no, let me take some time. The answer that you get, that we talked about last time, I'm not going to write it down, did take into account that we have gravity here. If you recall, it came into the definitions of the cutoffs. It cared that you had ADS2 here and so on. Any other questions? Yes?
Can we go over the three scenarios?
The three scenarios. Okay, so the first scenario was information loss. I don't know if that was the first one, but that's one of them. That's when you say that the state at late times is not pure, where the entropy of the radiation is large, but the entropy of the black hole is at the thermal entropy. Okay? If the state is pure, then the two entropies have to be equal for all time. Okay. So that's number one. Number two is remnants, or rather overfilling. It's the case where you say that this Bekenstein-Hawking entropy doesn't mean anything, let me ignore it, that the entropy of the black hole actually also grows with the radiation. Okay? That means this black hole of some finite mass can have an infinite amount of entropy. Okay? And this would hold for a black hole of any mass, even if it was tiny. In a more realistic system, a black hole would evaporate and get smaller and smaller and smaller, while the entropy just grows and grows and grows. And so it seems like that your theory has arbitrarily small energy or small mass objects with an arbitrary number of states, which is just weird. Then there was three, unitarity, I think, which is to say that that the entropy actually does that, and it follows the so-called page curve. But if that's the case, then I discussed the firewall paradox that results from this. In essence, because the mode that comes out, in order for the entropy to not increase, this thing has to be not entangled with that guy. But we derived before that the vacuum state implies that these two guys are entangled. Hence, if they're not entangled, you don't have the vacuum state. So it's going to be an excited state at the horizon, and that's the firewall. So this is our catch-22.
Information loss is bad, or it's just we're looking for a theory where everything's unitary?
Yeah, we're because of ADS-CFT, we expect that this system that I was drawing here is dual to the quantum mechanics of this dual theory, which are just quantum mechanical systems governed by Hermitian Hamiltonian with unitary evolution, and so we should respect unitarity.
Okay, so but in a different gravity theory where there's no quantum mechanics dual, then information loss is okay in that.
No, I will. Well, how about this? Well, the only scenario. So The only scenario that doesn't take input from anything is this scenario. If for a black hole in flat space, okay, the standard calculation would tell you that the black hole has an infinite number of states. Like technically speaking, I don't think anybody knows, for example, what happens at the very end of the black hole. Does it actually disappear and it's just not there? I mean, it's a guess. But the most careful calculation would say, well, you just stop before that happens, and you say you have a small mass object with an infinite number of states, or rather, a very large number of states, arbitrarily large.
Could you repeat the firewall proposal just once?
The firewall proposal, just the fact that this guy has to be entangled with this guy in order to have the vacuum at the horizon, but it has to be, well, in order for the entropy to stay constant, it has to be not entangled with anything. And those two statements contradict each other. Yes?
Does the firewall exist from the beginning, or it starts from Princeton?
Nobody knows. So in this particular situation, because of time symmetry, if it's somewhere, then it's everywhere.
So in this proposal,
I need to start going through the material. Okay. Thank you. All right. Unless because this is the last talk of the day, I can go over. I'm looking at. Okay. All right. Okay. Now let me give you the solution, and then I'll talk about how to derive it and justify it. Okay. Let me define the so-called gravitational fine-grained entropy. Okay. Suppose we want to compute the entropy of the following region. It's called a Q. It's a region that starts somewhere on the right path and ends on the boundary of ADS2, as in it actually touches it. Okay. The proposal is that the entropy of Q, the entropy of Q is equal to, well, what can it be equal to? So it's the standard von Neumann entropy of Q. So that's what Hawking would have said, or just a sensible person would have said. But now what we're saying is that you have to include another region, sigma x. It's the entropy of Q union sigma x, plus phi naught plus phi of x divided by 4 g Newton, where x is some point in the bulk, and sigma x is the region connecting x and the boundary of Q. Okay? The statement is that one should consider that in this formula, what we want to do is we want to compute this functional where we introduce this location x, where x technically is the location that is homologous to the boundary of Q intersection with the boundary of ADS, where homologous means that there exists a space-like codimension 1 ADS region, sigma x, that is bounded by the union of x and the intersection of a boundary of Q and boundary of ADS. Okay? So the sigma x is bounded by x and this point.
Left-hand side doesn't depend on x.
Wait, so what happened? What happened?
The right-hand side depends on the choice of x, and the left-hand side doesn't have any x.
Oh, this side here?
Yeah.
Yes, okay, good, thank you. We'll get there, we'll get there. So far I'm just considering this functional for some x. Okay, I didn't tell you what the x is. Was that the only objection, or were there more? Yes?
So this union is this point exactly?
The union of x and this thing?
Or or what is this dq and the ADS? This is this point and the
So what?
vertical line?
So what I'm now? So yes, it's this point. No, yes, this thing is this point. That's right.
Okay, then the space like is this line that connects between the two?
Yes. So what I'm doing here is I'm considering an x in the bulk that is homologous to this point. What do I mean by it being homologous? I mean that there exists a sigma x that is bounded by x and that point. Good. Okay. So now how do we fix x? Yes.
Is this like the generalized entropy?
So far, this expression is the generalized entropy of, let's call it of x, okay? Or rather of the entire region. Okay.
Sigma x would not need to be extremal?
Yeah. So now, what fixes x? The thing that fixes x, that fixes the location of x, is that you need to extremize over x.
But why is there a unique sigma x?
Why is there a unique sigma x? Why is there a unique sigma x?
If it's extremal, then it's unique.
Just in the
Because you have, don't you need non-trivial topology for that? Okay, I don't have
just
to
define x. X is a point in the interior, right?
Yeah.
Which is where there's a space-like curve to the boundary.
X for dimension 2. Such that x is homologous to that point. And the definition of homologous is this.
Which means that there exists a space-like curve that connects x to that boundary point.
Yes.
But no other constraint on that space-like curve. Why couldn't there
Correct.
be more than one?
I mean, there is more than one in the sense that I can consider something like this.
Yeah.
Yeah. It doesn't matter which one.
So when you extremize,
Yes. The way you.
that depends on x and sigma.
No. So all it depends on is Q. So we fix some region here,
Yeah.
and then we move x around, and we extremize this functional. And the reason why it doesn't depend on sigma x is because this entropy doesn't care about unitary transformations that happen within the region. And the dilettante here is evaluated on x. Okay, so this is what you have to do. But there can be multiple, there could be multiple extrema. Okay? So maybe this is an extremum, maybe point here is an extremum. In that case, you have to minimize over the extrema. Okay? Let me also give you another example that is homologous to this point, but is in a different homology class than what I drew here. I don't know if the phrase I used actually is the correct phrasing. Something like this, where x now has is disconnected. It's composed of 3 different points. Okay? Where now sigma is the union of this region and this region. But the point x, the set of points x are homologous to this point. because there exists a sigma x that is bounded by x and that point. And that's the union of this guy and this guy.
Can you draw it in the cigar configuration that you had for that? You had a part which was flat and a part which was radius to right?
Yeah.
In the cigar. So how do you...
No, but this is a, I mean, I can, you mean, I mean, it's gonna look the same. And something like that, maybe, on a slice. Yeah, but you should now just, this formula is really adapted to Lorentzian.
But the left-handed piece is a point in the interior, the cigar does not see.
Yeah. This thing is not, you can't represent this guy on the cigar. This is just an example that looks like it. Okay.
So x is a one point, or it could be any set of points in the interval?
X could be, candidate X could be any set of points, such that they satisfy this homology condition. Okay.
In that case, you will add this phi of x. If you have...
Oh, yeah, if you have multiple points,
Yes.
then this term here is the value, is a sum of the phi of x at all different points. And the entropy here is the entropy of Q union all of the sigmas. It's not a sum, it's the entropy of the sigma is the entire thing. Okay.
Well, what would be a point x which is not homologous to that region? Boundary of Q intersection boundary of radius.
Is it connected by time, like?
For example,
Or an even number.
or an even number of points. Yeah.
I'm sorry, so you define a function, s of q, which
Yes.
I'm sure is defined such that in the regime that you want it to behave in a certain way, and then it will behave in a different way than the previous one. But what's the reason that you expect this to be the unity of the radiation of the record?
Yeah, so far, I'm giving you the answer, now I'm going to derive it. This is just for the purpose of pedagogy.
So just to add another question.
Yes?
The number of, what you said, the number of x would be always odd?
Odd, yes.
Oh, okay. There will be always this line, and
Yeah.
then...
So the even, oh, it's clear you can't do it. Okay,
Yeah, sorry. Just,
Yes?
Just one thing. The other point you drew, you can still draw sigma x from that point to the boundary of Q, right?
sorry, when I have an even number of bulk points?
Um,
You can't, you should try it on your notebook.
yeah, I see.
Okay?
Has to be split.
Okay. Okay. Let's compute, well, okay, let me just schematically tell you, or go over the calculation of a single Q. So I think we need an eternal black hole stamp. Okay. So just by time transition symmetry, the point x is going to be at the same time as the endpoint of the point Q here. Okay, and the
At the minimum, extreme.
yeah, sorry, the extremum is going to have to be there by symmetry. Thank you. And so the only direction we need to extremize is really this direction. Phi goes as 1 over, let's call this point A. Phi goes as 1 over tangent hyperbolic 2 pi over beta times A. And the matter entropy of sigma x union Q goes as C times log of something like sine hyperbolic of A plus B over beta. There's a pi in there somewhere. I'm sine squared. I'm sine hyperbolic of A over beta. And well, all we have to do is extremize. This thing here is called it's called Sgen. Sgen is just the sum of this term plus this term. It's a function of A equals 0. And oh no, actually let me be a bit more careful. This is d phi divided by g Newton plus c times d on s has to equal to 0. What this means is that we need, well, 1 over g Newton presumably is much larger than c. Okay? So what this means, well, the only way that this is going to be equal to 0, this is some just order 1 number, is at d phi, the derivative of phi goes as g Newton over c. And what this entails is that what does the profile of phi look like? Phi looks like this. So starting from the origin here, it from where the horizon is, it starts, I think, quadratic, and then it grows. Okay. S does something else, but the only point is that the derivative of phi is small, so this means we're very close to the event horizon, to the bifurcation surface. So we're somewhere here, basically. Okay? That's where this thing is. Okay. Anyways, that's the calculation. That's so you can find it. Let me call this point B. But the interesting output from this calculation is that is the relation between A and B. A is equal to it's roughly equal to B plus beta times log of S black hole, the thermal entropy, S16 Hawking, minus S naught. Okay? If you think B to 0, phi naught over, this is phi naught over 4g Newton.
B was just the phi cube.
Yeah, exactly. Now let's take B to 0. Okay. Let's take B to 0. Something interesting to point out is that the location of A corresponds, if you measure it sort of in retarded time, it's a time which is given by, it's minus this, minus, let's say this is at t equals 0. It's at a time which is minus beta log S thermal minus S naught. Okay? This is known as the scrambling time. Okay, so we're going to come back to that later.
Which coordinate? In the y coordinate?
Yes, time as measured in the y coordinate. I guess I call that u maybe. Yeah. Yes. Okay.
You don't lose any generality by restricting to A instead of all over space-time X.
What do you mean?
I mean, you told us that you need to extremize over all of the points of X.
Correct.
There,
Correct. I'm only looking at one contribution. I claim that this is the dominant one. So there's a minimization, and I claim that this is going to be sorry, no. At the current moment, I know for this particular example, yes, this is the dominant one. And in fact, actually, if I think a bit more about it, I don't think there are any more. I don't think there are any more extrema. Yeah, I don't think there are any marks here.
So the units here for Gn are set by the radius, the ADS radius?
See that again?
The units for Gn are set by the ADS radius here?
Well, in 2 dimensions, G Newton is actually dimensionless.
Oh, okay.
No. Or rather, phi over G Newton is dimensionless. Is that right?
Okay, but in what sense is it large compared to C?
What is large is phi over G Newton. Or rather, phi naught over G Newton. No, both. The entire dilaton over G Newton is large everywhere. Okay, so that's one case. Another case is to consider the, let's do the following. Let's compute the entropy, not of 1 Q, but of 2 Qs. Okay? And so the first thing to do is to list all possible x's. Okay? And okay, we're not going to do all possible x's, we're going to do the 2 simplest. There's the obvious one, which is just like this one. So I can do something like this. It has 2 pieces, x1 and x2. And now we have to extremize the location of x1 and x2. But there's an even simpler one, which is also homologous to the 2 boundary endpoints. Now notice that the union of the x's are homologous to the 2 boundary endpoints. Okay? Because each one is. Okay? But another example is this, which is the case of the trivial x, okay? Or sometimes called the trivial surface. Okay? Let's consider this case first. Let's compute the generalized entry for the generalized entropy for this case. There's no x dependence, so the generalized entropy for this case is just a standard entropy. So S trivial is just equal to just S the standard von Neumann entropy of the CFT, which is what we called before just S of radiation, or rather the complement of S radiation, if you remember. Let's imagine we're working the limit where the size of Q is very small. Okay, so let's draw it like this. Remember, by complementarity, by the purity of the global matter state, the entropy of what I drew here is the same as the entropy of the union of the 2 baths that we talked about before. So this is one contribution, and you can study it as a function of time. And it's what we saw before, it just grows for all time. Good? Okay, so that's one contribution. Another contribution is this one that we started with, x1 and x2. Okay, so this is a bit more complicated. The reason is that it involves the entropy, well, it's entropy of the union of 2 disconnected surfaces, rather just a disconnected union. And that's a 4-point function of twist fields, as we discussed. And the answer is not known in general. It's only known in some limits. It's a property that if you have CFT, and you have O x1, O x2, O x3, and O x4, then in the limit, as x1 goes to x2, or rather x1 is close to x2, and x3 is close to x4, actually you only need one of them maybe, this thing factorizes. Into the product of two two-point functions.
So where is this x1 and the other 2 points?
This is a general statement.
Okay.
This is a general safety statement. Okay? And the same thing happens for the twist fields. Okay? Okay. The claim is that if you consider the solution that we found here for the location between the location of A, that at late times this property is going to be true in the sense that this point here, let's call this A1, or let me say AL and AR, and this point here is little br and little bl. If we just take the answer that we found for the single interval case and consider the entropy of the Q's at very late times, it's kind of manifest in this picture that these 2 points are closer together than these 2 points, or than they are to the other points. Okay? And in fact, they well, yeah. So okay, that's the statement.
In general, you have to write a sum over the conformal blocks of 2 3-point functions. So why do you claim that it turns into product of 2-point functions?
So I'm just making the following claim: that in some limit, when the two pairs of points get close to one another, well, one pair is close to each other, another one close to the other. Imagine doing the OP expansion and just restricting to the identity. Okay? Not the identity block, just the identity. And it factorizes in this way. And I'm just making the observation that at late times here, it satisfies that criterion. Okay. So this is the general behavior that we expect. You can try this for certain examples of CFTs, very simple CFTs, where you can actually compute this 4-point function, and it agrees with this expectation. But the interesting thing is that, I guess I didn't emphasize it here, because d phi it needs to be very close to the horizon. The entropy, the generalized entropy of this thing, is actually very close to the thermal entropy of the black hole, because phi is very close to the horizon, and the matter entropy is actually not very large. Okay? The volume entropy of the CFT is small compared to this term. Now going here at late times, it's just a sum of 2 of that guy. One for this side and one for that side. And so this predicts an answer. Well, we don't know what it is at early times, but at late times it predicts an answer which is twice times the thermal entropy. Okay? These are these are contributions of 2 different extremal surfaces. One of the trivial one is extremal by default. And so it's the minimum between these 2. So let me draw this here. Something like that. Thermal. And so the minimum between these 2 looks like this. Okay, so we get the page group. Yes?
So you said that the 4-point function factorizes when the 2 sets of points are far from each other.
Yes.
But you also said that when you extremize, you find that the A is near the bifurcation surface in both cases, so
Yeah.
they're going to be close to each other.
No. So this point and this point are close because they're almost like at least in this frame, they're almost like null separated. Similarly there, but that doesn't mean that this point and this point are close to one another. Just the fact about Lorentzian space. You can have 2 points that are almost zero distance from a third point, but the distance between them can be as large as you want. Yeah? So, sorry.
How do you use this kind of formula?
Oh, I just said that in order to do this calculation completely honestly, we need to know what the 4-point function is. Why? Because we need to evaluate the generalized entropy, which involves the entropy of the union of the two sigmas. Right? The two sigmas and the q's. But that's the entropy of the disconnected region. In order to compute the entropy, we first need the 4-point function of the twist field, which is, I guess I forgot to call it the Renyi entropy. And this quantity is not known in full generality, in general theory. But in simple theories, you can do it. And so what I'm saying is that I claim that at late times, for general theory, we do know what it's going to be equal to, because you make the observation that if you assume that it factorizes, okay, then you find that there's a regime where you have this OPE limit, okay? But I don't know if that term is familiar to you. You just have this limit.
What do you get? What is the result?
Oh, the result is there's just twice of what we got here. Because it I should have been more clear. Because the 4-point function factorizes, when you take the derivative, so these are two 4-point functions that depend on n, both of which, when you take n goes to 1, become 1. So you take the derivative, so you get the sum of two terms, and then you take n goes to 1, and then you get something non-trivial. You get the sum of the two matter entropies, one on this side and one on the other side. Maybe that was a bit too quick. Yes. Correct. The question is, how late is the late time? Okay. So you can ask. Suppose we assume this answer, the single-sided answer. At what time do I have this limit where these two guys are close together and these two guys are close together, but the pairs are far away from each other? It turns out that you don't need to wait that long. Just t of order just a few thermal times, or u, sorry. Some order 1 number times beta. You actually don't need to wait that long. So you might have worried that you need to wait a time of order 1 over g Newton or something. But no, you don't need to do that. Anyways, so then you minimize between the two and you get the page group. What else do I want to say about this?
What is the timescale for the tunneling? This.
Yeah, good. This thing grows as c times u times 1 over beta. So it's when this thing is equal to this thing. So it's when u is of order beta s thermal over c. Okay? So it's the usual thing. As the page time before an evaporating black hole also goes as the entropy of the black hole. Very good. Let me see. Okay, so that's cool. Now let's talk about one more example, a very simple example. Well, actually, let's talk about well, this wasn't the page curve for the thing that we wanted. Remember, we wanted the page curve for the radiation. The question? Sorry? Okay. Am I out of time, by the way? How much time do I have?
Till 5:30.
Oh, okay, good. So far, we got a page curve, but this isn't the page curve of the thing that we set out to compute. We wanted the page curve for the radiation, not for the black hole. Not for the union of the two boundaries, sorry. Okay, so let's modify this slightly. Let's compute the entropy of the union of these two regions. This is the thing that we set out to compute before. And it also had a trivial, the calculation that we actually did was the case where it was a, which in our terminology now corresponds to the trivial surface, in the sense that we don't include any regions in the bulk, okay? Any x's. If you compute the entropy of the union of these two endpoints as a function of time, then you will get this entropy that grows forever. So did this answer your question?
So what's the definition of Q to begin with? What is the question that you came with?
Here, the question was, what is the entropy of some region in the bath? Q represents a region in the bath.
This generalized entropy is tailored to this JP case? And
No.
Also
It's very, very general. I don't know if I finished answering your question.
So what you're just calculating is not equal to that because of the Q?
So, yeah, so I was gonna, well, okay, let me just say one thing. I don't know if this addresses what you want. So here, yeah, maybe I gave the wrong impression, but I'm only looking at Q's that end on the boundary. Is that the issue?
Yeah, I mean, because the left-hand side is S of Q. What do you?
Okay, so let's modify things here to choose Q to be some region like this. Okay? And now let's consider surfaces that are homologous to this region. Surfaces that are homologous to this region, this one is not homologous because it ends there. This region is now homologous to this Q. Okay?
in this case, when you write the formula, do you mean in the sense that the left-hand side is the exact S of Q, but on the right-hand side, when you compute the von Neumann entropy, you mean the von Neumann entropy like in some effective theory sense?
Yes.
Otherwise, it sounds like otherwise it sounds like a double counting.
Correct. That's why I guess implicitly I forgot I didn't clarify myself. Implicitly I put one Vn here and I didn't put anything there.
Ah, that's what
Yeah. And here I was just saying let's consider this functional that computes something. You can call an entropy or whatever, and then we're gonna derive why it's the right thing to consider. But yes. Ultimately, this is going to be the exact entropy of this region, and this is going to be the entropy in the semi-classical state. Yes?
So in terms of the calculation that we actually did, why did we have to plateau?
The calculation that we actually did. How did we get this plateau here?
What's the reason we did it? In terms of
Yeah.
information paradox.
In terms of the information paradox.
Yeah.
Well, first let me ask you a question. Just in terms of the calculation, like here, it was just about independent of motivation. Was everything clear? Okay. In terms of information paradox, right now it's not entirely clear. Now the relevant calculation for the information paradox is now the thing that I'm going to do right now. Okay. Okay.
Sorry, why is this the relevant region? The one that goes.
This one?
Yeah.
So I don't know if you were there in yesterday's talk. We discussed how in the semi-classical, well, in Hawking's, when you apply Hawking's calculation here, and you just compute the entropy of the radiation, and by the radiation I define that as this region, and you evolved it to the future. We had this argument based on computing directly using the formulas for entanglement entropy. We also had this other intuitive explanation for why you expect the entropy to grow linearly with time, because you have these entangled pairs. That the region keeps collecting as a function of time at a rate which goes as 1 over beta. Okay? So when we did this calculation before, we just got an answer that keeps growing for all time. And same thing, it's the same calculation here. Okay? This is going to give us something that grows for all time in this fashion. So that's one possible contribution. But that mysterious formula there tells us we need to also include these regions in the bulk, well, x's, and consider those that are homologous to this region Q. The union of the Q on the integral on the two sides is Q. Here is a region in the bulk, or two x's in the bulk that are homologous to Q. Okay? It satisfies that condition over there. And as a function of time, what you're meant to do is find the relevant, you find the x1, x2 that extremize the generalized entropy. Okay? Thankfully, we don't have to do this again, because we just did it. Just by complementarity, why do I keep just saying complementarity? Just by, by looking at the complement. No, that's the word. By looking at the complement, the calculation is really exactly what we just did. The endpoint of the red region coincides with the endpoints of the black region in the bulk, everywhere. And so this means that the dilaton contributions, the phi, are going to be the same for the two calculations. But also the global purity of the matter state tells you that the von Neumann entropy of the matter in the black regions has to be equal to the von Neumann entropy of the matter in the red regions. So we just did the calculation. And so this is the answer that you get. Okay? Okay. One final thing. There's a notion in homography known as the entanglement wedge. It's the statement, let me just say it now and maybe I'll give evidence for it later. So what I'm saying here, ultimately is going to imply that some parts of the bulk is going to tell you how the bulk here, this gravity region, is encoded in this quantum description that this thing is supposed to be dual to. When we took this region to be very, very small, roughly speaking, what we're doing is something like this. So from the dual description point of view, when computing the entropy of the union of the left and the right, it's given by considering these red regions here in the bulk. And similarly for the black, it implies we need to consider this part deep in the bulk. There's this notion of subregion duality, question of what in the bulk is dual to what on the boundary. And in this case, the claim is that it's the sigma that we were talking about there. Okay? The sigma in the computation of the entropy of the red guy, which is this thing at late times, and this thing at t equals 0. This is the bulk dual of the union of these two boundary quantum systems. Applying the same logic to the complement, the bath, it would say that the part of the bulk that is dual to the thing far away is actually this sigma. Okay, this entire thing here. So things here are dual to the system far away, the radiation far away. I'm going to call this region the island. Okay? So in situations where the sigma is disconnected from the boundary, it is called an island. Okay, now let me, no, one last point before I derive it. Okay, suppose you throw a message. Now about the importance of the scrambling time. Suppose that you have this system in the lab, and you inject some message here. You acted some unitary transformation on it, and you inject some information. From the bulk perspective, that's like some particle that just, let's say, falls in like that. Okay? This system is coupled to this system. You expect that at some point, well, it's coupled to this system, and the bath system is much bigger than this system. It's an infinite system. You expect at some point that the information about what you threw in should be recoverable from the union of BR and BL. Okay? Question is, how long do you need to wait? Well, the time you need to wait is just the time separation from when you threw it, you threw the particle in, and until when it just escapes the entanglement wedge or the sigma of Q. We know what this time separation is. It's what we wrote down here. It's the scrambling time. So this is just log of, I'm going to call it delta S, which is S thermal minus S naught. Okay? And this number is actually motivated by quantum information considerations. If you have a quantum circuit that acts on n qubits in a k-local fashion, or where any qubit talks to any qubit, but through interactions that involve a few qubits at a time, then the amount of time that you need to wait in order for the information that you threw in to be completely scrambled in the system is the logarithm of delta S. And one way to diagnose, what it means that the information scrambles everywhere in the system is that you can recover the message from any part of the system that is more than half. Okay? It's something called an erasure code. Okay, those are just comments. Okay, now let me talk about the derivation after answering one or two quick questions.
What will happen at that time, at the horizon until?
What will happen at this time? It's a very short time.
No, at the time that the change in S,
yeah,
it became a plateau, something happened, right?
Yeah.
So what happened?
So far, what happened is that, well, we're going to see in a second. But so far, it looks like just the formula that captures this property, the entropy.
Let us ask about
changes.
what happens to the formula.
Okay.
So far, what is really happening?
Right. So far, it looks like nothing's
Firewall,
happening.
you told me what is happening.
Good. Good. So far, it looks like nothing's changing.
How do you know?
Yeah, I'm saying so far, it looks like nothing's changing because I drew the pictures. But now let me derive that, but also agree with you that it's even in the derivation I'm going to give, it's still a bit suspicious. So let me go through that. Okay, one more quick question.
Can you restate the subregion duality statement?
See that again?
Can you say again the subregion duality statement?
The subregion I'm interested in. Yeah. Yeah, so each boundary system is dual to its own sigma. Remember the sigma we talked about there? This is called the entanglement wedge, which is the region that is bounded by the boundary region and its extremal surface, x. Okay, so for example, this thing is dual to everything up to this point. Okay? By causality, it's also actually dual to an entire diamond. Causal diamond. Okay, so I didn't want to confuse you guys. Okay. Now let's talk about the derivation.
Actually, can I ask that question?
You have a question? Okay, here, go on.
In this picture, I guess if in principle there's some very complicated unitary that you could act in the bath region, that will like put an excitation in the
Yes,
island.
yes.
But then the excitation in the island can
Oh,
hit the,
sorry. The unitary on which radiation?
Sorry, is there a unitary, I guess, would there exist a unitary in the bath region?
On which bath? The union of the left and right, not just the right.
Okay, the union of the left and right,
Yes.
sure, which will put an excitation in the island, in principle.
In principle, but with the restriction that it doesn't change the gravitational dressing, blah, 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 things like that.
Yeah, sure.
Okay.
And then that excitation could propagate and hit, like, it will escape to the boundary, because it's outside the horizon, right?
Correct.
Is that not curiosity?
No, I don't see why. It will only be paradoxical if the unitary that you acted on was, let's say you acted on here, and the time it takes for this guy to get to Q is longer than the time it would take to get from here to Q. Do you see what I mean? Because, like, if I act something local here, let's say.
Well, okay, then it would be radically paradoxical, but even so, it looks like you kind of have observable violation of fault locality. Like you could do something and you can tell that something happened that looks local to fault.
Yes, but I don't think there are paradoxes. That's what you know about paradoxes.
Depends if you assume fault locality.
Yeah. Okay. All right. Okay. So. All right. So let's derive this formula. So let's consider the simple case of computing. Let's talk about the path integral one more time. The full path integral. So z is dg, and also e to the whatever ijt times also the matter z, function of g. This thing, let's just focus on, well, here it is. It's just a single z, so I'm not specializing yet. The thing that we did so far, we looked at just a saddle point contribution to this partition function, where we fill in this region here with ADS2. Okay? So we have just the saddle point. We just focused on the saddle point of having the disk topology in this region. In principle, you should, in this integral, you have to consider all possible configurations. Configuration that change topology and so on and so forth. But for now, we're actually not gonna consider those.
Sorry, what's the subscript n?
Matter, or CFT. So let's be a bit sort of careful in our calculation of entropy, and let's not fill in the geometry until the very end. Okay? So all we have now, that this path integral tells us to consider all configurations subject to some boundary condition on the circle. Okay? So this now is empty on the inside. On the outside, we have the CFT. Okay, let's consider the entropy of the region of one, the entropy of just one of the Q's. Sorry, no. Let me draw it here. Say we want to compute the entropy of a Q like this. Okay. Then the density matrix of Q is given by the following. Okay, that's the density matrix of Q. What it means, again, is that you have to evaluate the gravity path integral subject to the boundary conditions. But so far, I've written down a matrix. Okay? We need to compute trace rho to the n, rho q to the n, which is the thing that we talked about last time, which looks like this. Let me draw it like this. No, let me not do that. Let me do this. And so on and so forth, where the bottom line here attaches to that, and this one attaches to the one below it, and so on and so forth. You just a standard replicator. And you can convince yourself when you do something like this, well, this picture is just is really just one big circle. If the size of the circle on each sheet was beta, after you make these identifications, you just get one giant circle of size n times beta. Okay? Now, at this stage, we're computing a number. We're not computing a matrix. We're computing a number. Now let's fill in our favorite gravitational solution, the saddle point being ADS2. So now this thing is filled in. You can write ADS2. Okay, so now it's filled in. So this is the cover. But now let's go. To the branch cover, this quotient by n, and so then we will get a picture that looks like this. Okay, ADS2. So ADS2 with a branch cover. So this is now the branch cover. Okay, so there's actually okay. So it turns out that when you do this branch cover, this point here was fixed as a boundary condition, and then we knew where this point was. We called it B. It's here. But the point A, where this branch cut ends, is actually it's a label for the configurations that we're considering. And since we're talking about we're looking for a saddle point, this means that it must be the case that we're evaluating this by we're looking at the on-shell action. This means that, well, if it's on shell, it must be that dA acting on I is equal to 0. Okay, but what is I? I, JT, on the IJT on the branch cover, so which I'm going to call a MN tilde, or let me call it GN tilde, is equal to, in the same logic that we discussed before, in the thermal entropy calculation, it's N times IJT on GN singular. Okay, just like what we had before, plus a term that cancels the contribution, an N here, from the conical singularity. And the conical singularity comes from, well, it sources a dilaton term. Okay, so this, here I'm focusing, okay, good. So here so far I've only focused on the gravity part, but let me emphasize that when I say we go on shell, I mean we go on shell for the gravity and not for the CFD. So what we're doing is we're replacing this by e to the I. Okay, fine. And so on and so forth. Yes. G n, it's also a function of a, times z CFT gn. Okay? And, okay, so I here is given by that. But if you look at the log of the partition function of the CFT, this thing is just equal to, well, on mn tilde, ultimately it's just equal to the 2-point function of two twist fields at A and B. So it's going to be log of sigma minus A, sigma at B, and M. Technically speaking, this is not true, except at when at n very close to 1. Okay, technically speaking, it is only true in this limit. But this is the limit that we're interested in. We want to compute the entropy at the end of the day. And so then if you do this, and you take the derivative with respect to n of this term and of this term, the first term will just give you the area p, the dilettante piece. It'll be this. Well, before you take the derivative, trace rho to the n is equal to e to the 1 minus n times phi plus phi a over 4g Newton plus the von Neumann entropy of between A and B. Okay? That's the claim. And then when you take the derivative with respect to n, you just land on the generalized entropy. Okay? So that's how you derive it. And in the situation when you have multiple extremal surfaces, like let's say there were multiple A's that extremize I, then you have another term here with A tilde, and so on and so forth. And as you can see, there's going to be competition between these different terms. The one with the smallest S-gen wins, because this is 1 minus n, so this term is negative. I'm assuming that n is greater than or equal to 1. So that's how you get the minimality constraint. So again, extremality comes from saddle point. Minimality comes from competition between saddles.
Assuming the number is finite.
Assuming the number is finite. Thank you. Okay, so that's this example. So this is how it works. You get the answer that you want. What about the case where you compute the entropy of the radiation? What happens there? Any questions about this?
10 minutes.
That wasn't a question.
That's an answer.
So the calculation is done in Lorentzian, Euclidean,
Ah, good.
one to the other.
Good. Here, I did it purely in Euclidean. Okay? But then I continued the location of A and B to Lorentzian time.
So do you, in that case, are you assuming the microscopic is some sort of SSS matrix model?
No. I'm just working.
Euclidean, JT pattern?
Yeah, I am using the Euclidean JT path integral. And I'm only, but in this calculation, I only had to consider the disk configuration or disk topology. And ultimately, what you do is we need to continue B to Lorentzian time, because the state prepared on this slice is just a t equals 0 state. But you're interested in how the entropy evolves with time. So you take this B and you evolve it, you just continue to Lorentzian time, and not in this case, but in the case I'm going to talk about next, that causes A to also move to, no, actually, sorry, even in this case. When you move this to Lorentzian time, A also moves to Lorentzian time. But in this case, there's a symmetry, so it actually doesn't matter.
Do you ever need to worry about replica symmetry breaking?
Yeah, you do. I'll make a comment on that later. Okay, so let's say we want to compute. This will be quick. The entropy of this region, of the radiation. Okay, so what do? We need to go through the same process. You consider multiple copies. You don't fill it in until you're computing a number. So here, so this is the density matrix of the radiation far away. Then you consider the replica. You consider the Renyi entropy. I imagine I have n of these, and it's branched across this thing. And one possible way of filling this out is to keep the branch cuts outside and just fill this thing with ADS2. Okay. Another way of filling it in is to let me actually now draw the multiple copies of the boundary. Let's consider the case where n is equal to 3. Another configuration that can contribute is this thing. It's a 3-headed wormhole that connects the 3 boundaries. Okay? And let me label point here A, A1, and the point on the other side A2. This configuration for general n, when you take n near 1, you can represent as the emergence of branch points and a branch cut inside the ADS2 region. Okay? Where this is at A1, A2, B1, and B2. Okay? So gravity does the job for you. It generates this region here, the thing that we call the island, and through the same procedure as we talked about in this case, it's going to be the sum of the on-shell action, or rather the sum of this contribution plus e to this contribution plus e to the contribution. And again, saddle point fixes the locations of the A's, and minimality comes from the composition between the 2 saddles. What else? So let me make a comment about...
what is the description of that in your original Z? What is it?
In the original Z?
Yeah, in the first line.
Yeah, okay. Let's go. Let me write it here. Z is equal to the sum over saddles of e to the minus I saddle, evaluated on the saddle, times z of the CFD, evaluated on G saddle. In the limit as n near 1, this thing is the sum over x extremal of e to the minus n minus 1 times phi naught plus phi at x over 4 g Newton plus s for Neumann of q union sigma x.
N input. So the second line, what do you do with n? What is the sum of the...
No, n n is specified at the, so this is, so the thing that we want, sorry, we want d n, roughly speaking, okay, zn as n goes to 1.
Yes.
So there's really a zn there.
Oh, okay.
Give you fun? Okay.
So what you calculate is really Zn, and then in the end, this is what you calculate in gravity,
Yes.
and then you take n to 1.
Yes.
So you didn't answer my question.
Now, I'm getting it.
What is going on in terms of the
Yes.
original zero?
I'm getting to it now.
Okay.
So what this is telling you is that in order to calculate the entropy, you need to consider a saddle point or the path integral, and then apply on that saddle point some formula. Okay? This is just evidence that maybe perhaps this saddle point is really what is happening in the real black hole, and it describes what an infalling observer would see. It's just evidence. However, what makes me uncomfortable about it is that it's not the output of a calculation that says what happens when you fall into the black hole. That wasn't the calculation that we wrote down. It wasn't like the expectation value of an operator behind the horizon. What is it equal to? It wasn't that. It's some other calculation. It's the entropy calculation. And so you can just take it as evidence for now, but it is just suggestive that perhaps the standard spacetime is there, but you now have to live with this non-locality, that the inside of the black hole is somehow dependent on things far away. I didn't talk about that, but if I just draw a picture, yeah. Consider the following thing. So let's say here we consider the overlap of preparing two different states, okay, which contains, let's say this state contains a particle of species 0, okay, or species A. And this is a black hole that contains a state, I act as an operator here, that has a particle of species B. These two states are orthogonal. Okay? Let me declare that. Okay? Or said differently, let's say it's a qubit, and here it's a qubit that falls in the state 0, and here's a qubit that falls in the state 1. The overlap of these two states is 0. But notice that I can bring another sorry, no, what do I want to say here? Yeah, okay. Notice that I can bring, suppose I bring a separate copy. Of the same thing. 0, no, not like this. Yeah, like this. 0, 1. These two states are also orthogonal. But let's do the following thing. Let's glue, so I think the following thing happens. Let's partition the path region into two parts. Let's glue these two parts here together. Let's glue these two parts here together. And let's glue this part here, this part here, this part here, and this part here. So what I've done is that I've interacted the two systems only on the radiation part, far away from the black hole. And what happens is that this interaction that I'm inducing on the two radiations, it amplifies the probability of a wormhole to get created that connects the two sides like that, where now the 0 state can contract with the 0 state here, So, and the one state can contract with the one state here, and hence you get an answer which is not equal to 0. But the upshot here is by the thing that we changed are things very far away, yet that affected the answer of things deep inside the black hole. So let me end there.
So other urgent questions? Okay, since people are tired. Let's thank Ahmed for giving 2 lectures non-locally in Israel today.
Yes.
So are the